Hello, my name is Tyler Walters, and this is my Unit 2 case connection. Today I'll be answering the Case 1 and Case 3 questions. So to begin, I'm going to move forward to the questions that are from Case 1, and those are, under normal conditions, describe all of the ways in which pyruvate kinase is regulated in this cell. And the follow-up question to this is in relation to isoform M2, which is a type of pyruvate kinase that is common in cancerous cells. And essentially what it is a molecule that doesn't exactly promote the glycolytic pathway or the moving forward of the glycolytic pathway, but I'll be answering that in a little bit. The second question to this is, what is the rationale for this mechanism, and what other pathways may cancer cells be diverting that substrate to? So to address the first question, just to give a little background information on what the regulation of pyruvate kinase actually is, there's two main pathways. You have the activating pathway, and then you have an inhibiting pathway. In the activating pathway, you'll see that fructose 1,6-biphosphate, which is an intermediate produced in the glycolytic pathway, is utilized in a feed-forward fashion to provide an allosteric interaction with pyruvate kinase. What this means is that the fructose 1,6-biphosphate, or FBP, binds to the activating site on pyruvate kinase, activating the molecule and thus encouraging upregulated production of pyruvate. So this is common whenever there's low energy levels within the cell. Obviously the cell is going to need to start getting more, like it needs more pyruvate, because pyruvate is a source of energy for the cell. So it would naturally, you'd see the cell wanting to move this process forward. And then, as mentioned earlier, the intermediate fructose 1,6-biphosphate is higher in concentration whenever there is lower energy concentrations or lower energy levels present in the cell. So say there's not as much glucose, say the body's not in a fed state, it's in a starvation state, that would be the time in which this pathway would be activating. The inhibitor, which is the phosphorylation of pyruvate kinase, occurs whenever the body does have a lot of glucose present, and that glucose has been broken down, and it essentially just doesn't really need a lot of energy. What happens is a intermediate produced in the glycolytic pathway, glucagon, begins to accrue in higher levels, and glucagon will in turn phosphorylate pyruvate kinase, thus inhibiting it in the same fashion of just the conformational change. And this in turn decreases the amount of pyruvate being produced and decreases the amount of energy present within the cell. So just a quick diagram of what this looks like. This specifically is for the activation or the allosteric interaction between fructose 1,6-biphosphate and pyruvate. At the top, you see glucose coming into the system. Fructose 6-phosphate's broken down by phosphofructokinase into fructose 1,6-biphosphate. Fructose 1,6-biphosphate then in turn goes through a series of interactions to bind to the pyruvate kinase, and in this it's not super clear in the depiction, but it does it does upregulate it given the positive symbols. I do not particularly like this diagram, but this is one of the better ones of the ones I found, unfortunately. Moving forward, I move into the second part of case 1, and that is in relation to the isoform M2. Type M2 of pyruvate kinase is ineffective at promoting glycolysis, as mentioned earlier. And in the question, this is intuitive. This is mainly because if you have a cell, like a cancer cell, that's actively trying to proliferate, trying to grow, trying to expand as quickly as possible, you're going to expect increased needs within the cell, especially because glycolysis is an extremely critical and essential pathway for most cells that undergo glycolysis. So the question is why would a cancer cell be encouraging ineffective glycolysis progression? And it's important to note that pyruvate kinase, the type here, is the last part of the glycolysis step, which kind of leads into the potential explanation. So the idea is that by encouraging the cell to go through glycolysis, you're going to generate the intermediates relevant within the process, and then by throttling it at the end, the intermediates are not getting used and can therefore be pretty much repurposed by the cell for other types of biosynthesis. Specifically, the one I found, I did a literature review on this topic, and I found that it seems to be linked to cell proliferation. There's not a lot of answers exactly into how this interaction works between the encouraging or the gassing of the glycolytic pathway and then the eventual throttling. But the general idea is that by generating these intermediates, they can be used in pathways relevant to cell proliferation, which would in turn be beneficial to the cancer cell because, as mentioned earlier, these cells are pretty much, I mean, if you put in layman's terms, their goal overall is to expand as quickly as possible, usually through, say, different mutations like a P53 or KRAS. And this has the cancerogenic effect, the oncoprotein effect, so forth and so forth. So just reviewing the two questions. Getting lost a little bit here. Pretty much, there's two different ways in which pyruvate kinase is regulated, the phosphorylation and the allosteric interaction, and then the idea is that the substrates are being diverted to cell proliferation pathways. Okay, so moving on to case 3. You have a patient basically presenting themselves with certain symptoms, which I'll review in a second. And the first question is asking about these symptoms and what might be the biochemical basis for these symptoms. Based off of this, what would I expect the patient's fasted glucose levels to be given in his current condition? Fasted meaning he has not had a glucose load, which is shown in the report given with the case. And then which two regulatory enzymes are likely to be active in this individual's current condition. So we'll go ahead and address the first question. The patient presents with a baseline insulin level of 0.8, and you're expecting, based on the control, for it to be around 6 plus or minus 2. What this means is that the patient quite obviously has a very, very deficient insulin level within the body. And then after the glucose load, you'd expect to see insulin to spike, and you do not. I mean, it does slightly, but not in a significant manner, especially considering it's a 5 to 40 ratio, plus or minus 11. So the first thing that draws my mind is, this patient's probably diabetic. If you look at the symptoms, you see that the patient's drowsy, thirsty, and has frequent urination. What this might mean is that the patient has very high levels of sugar in their body, and the possible diagnosis could be hyperglycemia. Those two pretty much go hand in hand, as well as with diabetes. So I'm expecting that this patient has an insulin deficiency, and because insulin in the body is responsible for promoting the glycolytic pathway and maintaining homeostasis or glucose homeostasis, the insulin's not really doing its job, and the body's not doing what it needs to essentially get rid of all of the excess glucose in the body, and in turn, it's resulting in this drowsiness and relevant symptoms related to having too much sugar in the body. So without having the insulin there to pretty much promote glycolysis, it starts to build up, mainly in the bloodstream, which is why they're pulling blood samples. And there's not a significant amount of regulation going on. The question brought up earlier is what would I expect the sugar levels to be? I pretty much mentioned it, but I'd expect them to be very high above normal range. And the two regulatory enzymes that would still be active in this situation, we can look at what we have here, which is GLUT1, GLUT2, GLUT3, and GLUT4. GLUT4 is insulin dependent, so it's probably not going to be GLUT4, because without insulin, GLUT4 is not really going to be activated or doing its job or promoting glycolysis. You have GLUT1, GLUT2, and GLUT3. I'm not really expecting it to be GLUT1 because GLUT1's common in fetal tissue, from what I was seeing. So, I mean, this child's not an infant, so I don't see that being present. And then GLUT2 and GLUT3 are the more likely ones because they're insulin independent, and they're active locations of the liver and the brain. I'd expect GLUT2 to be the most active. So yeah, that pretty much concludes my case connection. Thank you for watching.